Hello, I would like to introduce you to the homework that I'm assigning that relates to inner product spaces and norms. You may see the instructions here. Give short answers to each question. The answers must be in order. You may type or write your answers, convert to PDF, and upload to the course webpage, which is canvas.instructure.com. For converting written work to PDF, you may take a picture of your work and use the Cam Scanner app to convert. So I made a video to show how to do that. Let me remind you of the website. The website is Cam Scanner. Okay, let's see, I think you can't see it. Cam Scanner, Canvas, canvas.instructure.com. Alright, and that will take you to the website. You can type on your phone or on your computer. It will take you to the website and you should be able to log in. Mine has already logged in because I've stored my login information. Alright, so let's look at this sheet and these questions. Please notice that I have revised this sheet from the first sheet that I handed out. You will need the revised sheet. I will share on the Canvas webpage as well as on the WhatsApp group. Definition: a real inner product space is a real vector space with an inner product. An inner product is a positive, definite, symmetric, bilinear form. So in class on Wednesday, we spoke about a bilinear form, what that means, and I just got to talking about symmetric. I have sent the notes here through the WhatsApp group. I'll remind you of the idea of a bilinear form. First, we talked about a linear function. Right? The idea of linear relates to the idea of linear combination. Here I have a linear combination of two vectors, a1 times x1 through xn plus b1 times y1 through yn. a1 and b1 are constants, or we call them scalars, and this n tuple x1 through xn is a vector. It's an n-dimensional vector, and y1 through yn is also an n-dimensional vector. We represent vectors as arrows. You may have seen these diagrams, especially if you've taken physics. So I have here two-dimensional vectors with an angle between them. Inner product is related to angle. There's an inequality called the Cauchy-Schwarz inequality that says that the inner product of x and y, and I'll define this in a moment, x comma y, what that means, divided by the length of x times the length of y is less than or equal to 1. Here when I talk about the length of x, I use the common length that's associated with the Pythagorean Theorem. You know, Pythagorean Theorem says a squared plus b squared equals c squared. So that means that the length of the hypotenuse is the square the square of the length of the hypotenuse is the sum of the squares of the lengths of the sides. So that means the length of the hypotenuse is the square root of the sums of the squares of the lengths of the sides. So Euclidean distance is the sums of the squares of the particular components in different directions. In two dimensions, x1 squared plus x2 squared, take the square root, gives you the length of x. In n dimensions, we have the same rule. So we have n-dimensional length. Okay. So we use the Cauchy-Schwarz inequality to define cosine of an angle in terms of the inner product. So you can see here the relationship between angle and inner product, or rather cosine of angle and inner product. Okay. Now, the bilinear form is a generalization of the usual idea of inner product. So let's start and see what bilinear form means. Now, bilinear form is a function. A function takes some number or set of numbers and produces another number or set of numbers. Okay. Any function has a domain and a codomain. You may be familiar with domain and range. Codomain is a generalized notion of range. A bilinear function has a domain of v cross v. That is, it takes two vectors. That's what the cross means. I take one vector from a vector space and another vector from a vector space. So a bilinear form has two vectors as its domain, and it creates a real number as its output. So really we have two vector inputs, one real number output. The function is written this way: b parenthesis v and w, to emphasize the fact that b takes two vectors and creates a single output. All right, so we continue with this. Now, we are trying to get at the idea of bilinear, so I try to help motivate the idea of what linear means. All right. A linear function satisfies an algebraic equation. So this algebraic equation is related to geometrical properties. I mentioned that a linear function in one dimension corresponds to a line through the origin. Now notice a line that is not through the origin is not considered as a linear function, even though the graph of the function is a line. A linear function must have a graph which is a line through the origin. All right, so if we have this line, I wanted to consider these two quantities. If I take x1 and x2 as two values of x, and I said, well, if I take f of x1 and f of x2 and add them together, what's the relation between the result and f of x1 plus x2? We did some examples. If I say f of x equals 5x, that's certainly a line through the origin. In this case, when I computed f of x1 plus f of x2, using substitution, I found out that in this case, f of x1 plus f of x2 is equal to f of x1 plus x2. Okay. Similarly, we found that if we take f of x equals ax, where we don't just use 5, we use any constant, we can use a, we still get this same relationship. F of x1 plus f of x2 equals f of x, this should say f of x1 plus x2. I'm sorry, this was a mistake. Okay, I fixed the mistake now. So here we take f of x1 plus f of x2. This is the sum of the function at different values of x. We can generalize this expression by taking a constant times f of x1 plus a constant times f of x2. And we found out that when we do that, the constants also go inside the function like this. Okay. And we found in general that if we take c1 times f of x1 plus c2 times f of x2, which we have right here, we get, and we use substitution, we get f of cx1 plus c2x2. Sorry, f of c1 x1 plus c2 x2. Right. In fact, this is the general linear property. That's what it means to be a linear function. And you can see linear function is closely related to linear combination. You could express this as a linear function of a linear combination is a linear combination of the function values. Let me type that down here. That may be a useful way to remember this. So a linear function of a linear combination is equal to a linear combination of function values. All right, here you have linear function, which is applied to a linear combination of vectors. Now I should probably put the vector sign over those vectors. I'm sorry that I do forget that sometimes. Let's go ahead and do that now, because these are vectors. Typically I will use x to denote vectors, and in this case the subscript means I have two different vectors, and I will use a ABC to denote constants. All right, so this is a linear function. Now we want a bilinear function. Remember, a bilinear function has more than one vector as its domain. Right, so before we did bilinear function, I also did example of 2 dimensions. A linear function in 2 dimensions is represented by a plane, which is this pink set, the plane through the origin. And I tried to represent this plane. We looked at the standard basis. If we look only along the standard basis vectors along x1 and x2, the plane will look like a line. So this same linearity relation for a line also holds for vectors in a plane. We looked at some examples there. Right. Now, bilinear, as I said, bilinear is not just a function of a single vector, but it's a function of 2 vectors. And a bilinear function is linear in both of the vectors separately. So I really can have 2 relations here. If I look only at the vector in the first place, which in this case is c1x1 plus c2x2, you can see that here I have b of a linear combination of x's, and the result becomes a linear combination of the value of b at the different x's. And the same with y, right? So we have linearity in both of the vectors which consist of the bilinear form. All right? All right. And we showed that, in fact, if we take the usual inner product, which is defined this way, x1y1 plus x2y2 plus x3y3, and I tried to emphasize here that in this case, x1, x2, and x3 do not represent different vectors, but different components of the same vector. In math, just like in any language, you need to pay attention to the context. In the context here, I've made it clear that x1, x2, x3 are not vectors, but they are components of a single vector, a single 3-dimensional vector. Same with y. y1, y2, y3 are not vectors, but they're components of a single vector. Okay, y1, y2, y3. Right. So we can check this bilinearity condition. There are 2 bilinearity conditions, and since I'm using x1 and x2 as components, I take my 2 vectors as x. My 2 vectors are x and x prime. So there's x, and here's x prime. Okay, and we went through this derivation, and we showed that, in fact, the linearity condition works for the x's, and it works similarly for the y's. Okay. Now, symmetric means that if I take b of x and y, this is the same as b of y and x. And unfortunately, my computer ran out of battery before I was able to finish this. But we could do some example, very simple example. If I take b of x, y is equal to the usual inner product, because that is one particular example. Let me take the inner product in 2 dimensions, x1, y1 plus x2, y2. And this is on R2 cross R2. Okay, I have two two-dimensional vectors. Okay, so you can verify that b of x1 of x and y. Sorry, it's not working very well. Let's try that again. B of x and y is equal to b of y and x. You can verify this. Okay. Now see, because you can see that if I write x1, y1, that's really the same as y1, x1. x2, y2 is the same as y2, x2. So I really can exchange the x's and the y's without any change. So that's symmetric. The last property is positive definite. And this property can be expressed as b of x with itself. All right, remember, I have two vectors as my arguments of b. So I can take b as with itself. That's going to be greater than or equal to 0, and b of x equals 0 only if x itself is the zero vector. Okay. So here I always get a non-negative number when I take b of xx, and when the result is 0, I only get 0 when the vector x itself is the zero vector. Okay, so that's the complete introduction to a positive, definite, symmetric, bilinear form. Okay, and in the next video, I'll review the problems that we will be talking about in this section. So thanks very much for watching.